Let's see. Okay, yes, we're actively recording now. So we're going to start off with Bailey. He is going to give her a devotional and her presentation on Ubuntu. Take it away.
All right. So for my devotional today, I picked Romans 5, verses 1 through 5. Therefore, since we have been justified through faith, we have peace with God through our Lord Jesus Christ, through whom we have gained access by faith into this grace in which we now stand. And we boast in the hope of the glory of God. Not only so, but we also glory in our sufferings, because we know that suffering produces perseverance, perseverance, character, and character, hope. And hope does not put us to shame, because God's love has been poured out into our hearts through the Holy Spirit, who has been given to us. So basically what I get from these verses, especially right now, is that our suffering has a purpose, and suffering makes us better, and that God's not just throwing all this at us because he has some goal for someone else that he's accomplishing, but also a goal for ourselves that he's accomplishing. And that helps me get through day to day right now. Does anybody have any thoughts about that?
Yes.
All right.
Definitely a nice devotional and something that at times can be hard to do until we remember to focus on God, right?
Mm-hmm.
Okay.
It's hard to focus on much of anything now.
Yeah.
Yep.
You think it might get a little bit better once classes are done for the semester?
I think it'll honestly get a bit worse.
Okay.
Because there won't be anything to separate one day from another.
Right, to focus
Yeah,
on.
after classes, I had no idea what to do throughout the summer at all. Like, I had no idea.
Yeah.
All right, so last time Jason covered the history and different flavors of Ubuntu, and today I'm going to be covering the file system and GUI. Most of the Linux distros are pretty much the same when it comes to the kernel, and I was having a lot of trouble finding anything on the kernel that I could actually understand. So I'm covering the file system because that actually can be different between Linux distros, and the GUI, which is usually one of the biggest changes between Linux distros. So Ubuntu follows the file system hierarchy standard, mostly with a few deviations, and the Ubuntu webpage didn't list exactly what those were. The directory names are not like the ones in Windows. And unlike the Windows file system, Unix and Linux use forward slashes instead of backslashes. I like that better because it makes it easier to type file paths in, but that's just me. The backslashes are used to escape spaces in the directory or file names. And there are 18 important directories in the Ubuntu file system as listed on their website. The main directory is denoted by just a forward slash. The file system hierarchy standard refers to it as a root directory, which is not the same thing as the root directory of the home user, which is actually contained within the root directory, as are all the other directories on the file system. And I pulled all these slides from the Linux file system tree overview page on the Ubuntu help page, and from the file system hierarchy standard for explanations. The entire system is contained within the / or main directory. Bin holds the terminal commands, and it contains the essential user command binaries like cat, umount, copy, and make dir. Boot holds all the files actually needed to start the system, such as the kernel and the bootloader. Dev holds the files that represent things like hard drives, but not the thumb drives. Those go somewhere else. etc holds the global configuration files. Home is just like the user directory on Windows, pretty much. It holds the downloads, documents, pictures. It's what users normally use on a regular basis. A normal user on a computer is not probably going to go outside of home unless they just really like messing around with the file system. Lib, as its name implies, contains all the libraries and kernel modules. Media is the mount point for the external devices like thumb drives. MNT is another mount point, but that's temporary mount points like file systems. In the Ubuntu subsystem for Linux app, this directory includes all the Windows directories, so you can actually access all your Windows files from the Ubuntu app. Opt has the additional software that isn't covered by the package. This should be manager. Proc handles processes and kernel information, and it's another directory that holds files that aren't actually files per se, but other things being represented as files. And root is the home directory for the super user. Run holds the runtime data during boot. It acts like a temporary file system, and it's not used any other time but boot. sbin is the bin folder for the super user because all the super user stuff, or at least a lot of it, is separated from normal user files. Server handles internet-related things like protocols and stuff. Sys shows the kernel's view of the system using a virtual file system. Temp lets applications have a place to store temporary files. User holds most of the user's applications, things like that. It also has duplicates of some of the other directories specifically for that user. var handles items like logs and email files that you don't want to go away between boots. So that was the file system. The GUI up through Ubuntu 16 was a custom Ubuntu designed desktop called Unity. Because of monetary reasons, they switched to GNOME, which is separately maintained, and they switched app stores along with the desktop. This brought some pushback from users, but it's pretty easy to change which desktop you're using on Ubuntu. So the users who really didn't like it were normally techie enough to just do that. Both app stores were very difficult to use and often don't work. So that wasn't too much of a change. Here's the Unity desktop. And this is what the new GNOME desktop looks like. The GNOME desktop lets you have an activities overview, which is what was displayed on that screen, that has all of the applications and lets you search from them. You can choose to show just the frequent apps or all the apps. And it's like the start menu, but it's a full window. I'm not sure why the GNOME website is so excited about side-by-side windows, because pretty much every mainstream desktop has that now. The notifications are a new thing. Unity didn't have those. GNOME will put them on the desktop and put them in a list like Windows does, so you can come back and look at them later. the application menus change position, so you can get to it even if the window is minimized for that particular app. The dash bar used to be like the Windows taskbar, where it just has what you put on it and then a few default things, but they changed it so it shows your favorite apps now instead. The nightlight feature was something cool they added, because the nightlight now comes automatically instead of having to add it separately. It basically takes out the blue light in the screen. You can set how much it takes out, but that can really save a lot of eye strain, especially when you're programming for 8 hours a day. And here are both Jason's references and my references, in case you're curious where I got all this from. Does anybody have any questions?
We're great. Great presentation.
Thank you.
Yeah, so she mentioned the proc file system. That is a interesting virtual file system to peruse and take a look at when you get a chance, because it is a very valuable tool in a lot of the Linux distributions for debugging your code. So. All right, so that was Bailey's presentation, and that finishes up the Ubuntu. So Tyler Krautz is next. Is Tyler on the call right now? Yes, I haven't heard from him in quite some time. So Ethan, be prepared to present next time, basically on Monday, if because it's likely that Tyler won't be available. Let's see, is Ethan online here as well? Yes, he's on. So Ethan, be prepared. And then after that is Ian, and with Puppy Linux, and Cubes with John Cassetta. Then we have the Android, the Oxygen release with Timothy. And so I believe that should be all of the presentations. So if you weren't called out, let me know, because I think those are all the presentations that we have left. Okay. So the administrative items, Monday is the quiz on main memory. And then April 27th, the next Monday, we have the mass storage programming problem. And then May 4th is programming exercises, which are 10 extra credit points. And then Chapter 9 is virtual memory. I mean, Chapter 9 virtual memory. Actually, I think we are in hard disk, so looks like I haven't fully updated. But any questions about the assignments coming up? I think we mostly have the 2 programming assignments and mostly quizzes coming up, and then the final. Let's see, new message. Will there be a Star Wars theme extra credit question on May 4th? Probably not. Sorry, Jessica. Well, we'll see what I can do.
On Canvas, both Chapter 9 quiz and Chapter 8 quiz are due Monday. Is that still a thing?
Oh, no. I will move the other quiz till later.
Okay.
Yes, I'll take a look, but that should definitely be moved. Yeah, I'm thinking the virtual memory quiz will probably be like maybe Friday, Wednesday or Friday, but hopefully Friday.
Mm-hmm. That sounds good.
Yeah, actually, let's take a quick look. Let's see. For some reason, I can't see the dashboard. Oh, there we go. So, yes, I have them both due. Yeah, I will fill those in. So yeah, let's probably count on like Friday for the virtual memory quiz. So I'll give you two ends of the week for those two quizzes. All right. So on to the mass storage information. So previously we discussed the two scan algorithms. The scan, which goes from one end of the disk, from let's say the outer to the inner, and then goes back from inner to outer. That was one particular algorithm that could be used, looking through the cylinders to try to minimize the seek times. Another popular algorithm was the C-scan that we looked at, and that's where it goes to one end and then comes back. And that was to try to reduce the worst case seek times and have it so that you don't have long delays, that you average things out a little bit better. And that's because if it just started going from the outer to the inner and you're at the outer edge, you may have to wait for it to go all the way down to the middle and then come back up before you access. And so that could be a long time. So hence the technique of always going in the same direction and returning back to where you started from to try to reduce the average wait time. Or not the average wait time, but the longest wait time that you may have incur. So again, know these algorithms. And then CLOOK is a version of scan, but it takes into account that if it's traveling down, from outer to inner, say, traveling down the cylinders, and it gets to a point where it's looking ahead and it sees no requests that are in that direction, it can go ahead and continue. And then in the case of the CLOOK, it can actually then just stop and turn around and continue on the other way. It doesn't have to go all the way to the end if there are no requests for cylinders out that direction. So CLOOK is the version of C-scan, and then look is a version of scan. So again, both of those look ahead, and they are the analogous versions of looking ahead with scan and C-scan. Either you always go in the same direction or you go back and forth. So that's the way those algorithms work. So selecting a disk algorithm, how do you go about choosing which is the best? The SSTF, which was the shortest scan time, is common and has a natural appeal because you're reducing the amount of scanning that has to happen. But scan and C-scan can perform better for systems that place a heavy load on the disk, in that it's always being accessed, and so there you just keep the head moving all the time. So that would be for heavily used for systems that heavily use the hard disk. That can be advantage, as well as the fact that you don't have the starvation problem with the shortest scan time algorithm. And then, of course, the performance will depend on how the disk is being used. So again, depending on the cylinder accesses will greatly dictate how it performs. So it will be dependent on those actual accesses. So no algorithms can handle every single case necessarily the best. Things that can influence your decision is how you allocate files on the disk. So your storage mechanism, and so how it's laid out, how you pick where various information is located and stored, and it can heavily influence the algorithm use. And the other thing that's typically done is the scheduling will be written or contained separately from the rest as a separate module than the rest of the operating system, so that the algorithm can be replaced depending on how you're using the system. So you can actually choose the scheduling algorithm. The other thing that you can think about is it may depend on the hardware as well. What are some of the characteristics of your hardware and what does it do particularly well? You could also take that into account into choosing which algorithm you use for scheduling. So the text says that SSTF or look is a really reasonable choice for the default algorithm. What about rotational latency? That is difficult for the operating system to calculate, and it also has less of a deterministic value in terms of the latency, since it tends to be much quicker than the scan time, so or the seek time. So the seek time is the greater component. So generally, that's not usually done because of the complexity of the calculations and the amount of time the calculations will take. Generally, it gets swallowed up by the fact that it's fairly small to begin with. And then how you queue up your requests and things also can dictate how you might select an algorithm. So disk management is kind of an interesting issue. We have the low level or physical formatting, which is dividing the disk into the sectors and the tracks. Each sector can hold header information plus data plus error correction. ECC is the acronym for the error correction code, and this is extra information that's added to the data so that data can be recovered in case of failure of particular storage areas. That you provide redundant or error correcting information into the data that will hopefully allow you to recover data if it gets lost. Usually it's divided up into 512 bytes of data sections, but that can be selectable. In terms of using a disk to hold files, you generally have partitions. A lot of you have played around with multiple partition disks, and for instance, putting different operating systems on different partitions and things like that. And then there's the logical formatting of actual having a file system on top of the disk in terms of managing the files, in particular how your user applications and your users interact with the storage is typically through a file system. To increase efficiency, the file systems are grouped in blocks or clusters. And the text mentions that disk I/O is generally done in blocks and file I/O is done in clusters. So that's just sort of implementation mechanism for writing out data. And this is taking advantage of the fact that you typically access data sequentially through a bunch of section. And this is done to take advantage of that you go ahead and in anticipation, since it's quicker once you've actually done a seek to the right location, that you can access all the data that will typically be used and throw away if it's not. But from the fact of the way it's being used, you generally know that it's very likely to be the next data that's going to be requested. Raw disk access are for apps that want to do their own block management and keep OS out of the way. We already mentioned that databases is a very common example of that. And then you have to have the boot block, which is, we talked about that in terms of startup. It's for initializing the system. The bootstrap is stored in ROM, but the bootstrap loader, which basically the ROM will point to the bootstrap loader or tell the system how to get to the bootstrap loader, and the bootstrap loader is in a particular partition of the disk set aside for the boot process. And then there's various techniques for handling bad blocks, and the text mentions sector sparing used as one way to handle bad blocks, but that's basically setting aside an area that you start seeing failures on, that you could set it aside and possibly not use it. Again, these are details that we won't worry about, but just keep in mind those kinds of activities are being done. So your text goes through an example of booting from a disk in Windows. And so see here, we have the master boot record, which contains the boot code and the partition table. So the boot code is firing things up, the bootloader, and then it points to the partition table that shows the various partitions that have been allocated on the disk. Here we have 4 partitions, and then we point to the boot partition, which will then load the bootloader. So we had a sort of lively discussion or chat session about RAID structures and various schemes and how expensive some of the larger or some of the RAID schemes can be. So RAID stands for Redundant Array of Inexpensive or Independent Disks. Initially, it was to take advantage of inexpensive disks that because of being inexpensive, that you wanted to have some redundancies in case you have all kinds of a bunch of errors. It's to mitigate the impact of errors on your disk. But typically, disk quality has gone up to the point that now usually it's referred to as redundant array of independent disks. The I has now become independent instead of inexpensive. And again, we're using multiple disks, as I mentioned, to provide reliability via redundancy, that you can put redundant information across multiple disks, so that in the event of a failure on one disk, that you could possibly recover from information stored on another one of the disks in the RAID. Key thing is it increases the mean time to failure. The mean time to failure is what the average time is before a failure occurs in the hard disk. So you're basically trying to minimize or to extend the time or minimize the number of failures. So you want to make it so that you can run for longer periods of time without a failure. And the book talks about mean time to data loss based on various factors. But one technique that you can do that is least efficient is to completely mirror the disk, which is basically that you write the same data onto multiple disks, one or more disks, or two or more disks at the same time, and so that when there's a failure, that you know you can get the information from the other disk, or you're hoping that you can get the information from the other disk. Places where this can fail is if the failure is such a situation like a power outage. In the case of a power outage, you would suspect that, yeah, all of the disks would have that same failure, and so it's not foolproof certainly to mirror the disks. But you can see here that you do, and they work through the math on what you would typically, what types of mean time between failure improvements you can get by mirroring. Now, it's frequently combined with NVRAM, or non-volatile random access memory, to improve write performance. And then we also know that solid-state disks are also using non-volatile memory, NVRAM. And so you can see, hence, the move toward or the use of hybrids, which are solid-state and mechanical optical or magnetic media type disks, since so you can keep the cost down but still improve the performance and maybe even the failure rates. So there have been several improvements in disk techniques to have them work cooperatively. As many of you know and have seen, that certainly there are various classes of RAID 0, 1, 2, 3, 4, 5, and 6. So 6 RAID levels were listed in your text. And so, but please keep in mind a basic understanding of what we mean by a RAID disk, which is a redundant array of independent disks now. And then originally it was inexpensive disks. Oops. So RAID techniques, one technique is striping, which uses a group of disks as one storage unit, and it will actually store. Okay, Timothy has a question about RAID.
So what's the difference between like RAID 1? Oh, are you talking about it right now?
Yes, we will go into a little bit. So RAID 1 is a mirrored disk. So that was the first one we talked about. That's mirrored. And then RAID 2 uses memory style error correcting. It adds that capability. And then RAID 3 does bit interleaved parity. And so the text goes into those in, I think, a lot greater detail than I will. It's on page 488 through 490 is where in the text where they talk about the various RAID levels. But yeah, so mirroring or shattering, RAID 1 keeps a duplicate of each. RAID 0 is non-redundant striping, so that's just putting data across different disks. And then striped mirrors. So here we're actually mirroring the disk, but we're also striping. That's RAID 1 plus 0. And so basically you can combine different aspects you can see of the different RAID levels. The blocked interleave parity RAID 4, 5, and 6 uses much less redundancy. It says the text talks about how RAID with a storage array can still fail if the array fails. So automatic replication of the data between arrays is common if you're trying to drastically reduce the mean time between failure or the failure rate. And then also in RAID designs, you frequently have a small number of hot spare disks that are left unallocated, so you're not using them at all. And when you have a disk fail, that one has the data rebuilt onto them, and you actually rebuild the data and place it on one of the hot spare disks that are left set aside for recovery purposes. So again, we're not going to go into details about the actual intricacies and techniques, specific details about the techniques, but the text does cover that. So if you're afraid that you will actually get quizzed on it like Jacob did in an interview, you should definitely refer to that section or do some online research about the various RAID levels. So high availability data areas would be areas that you would be concerned about RAID or NAS, network address attached storage, and things like that. So you could imagine that you'd want to have some pretty solid understanding of things if you were, for instance, to work on the Netflix teams that's looking about streaming data. So one area would be the internet access and compression and things like that, about transferring the data, but also being able to store that large amounts of data that users can stream would also be useful. Also, online merchants like Amazon would also be an area that if you were in that particular area of the business would be important for you to know this information for. But other than what is RAID, I won't be quizzing you on the intricacies of the different RAID levels. So there's various extensions to RAID. ZFS is used by, let's see, I'm trying to remember which operating system that is. But it's a scheme. Oh, here it is. There it is right there on the second point. It's Solaris. And again, it's expanding on RAID, the fact that RAID does not prevent or detect data corruption or other errors, just disk failures. And so Solaris adds ZFS file system or RAID system, adds checksums to all the data and metadata to try to detect errors and to correct errors in conjunction with the use of a RAID set of RAID disks. The checksums are kept with a pointer to each object to detect if the object is the right one and whether it's changed. And like I said, with this information, it can detect and correct the data and even errors in or misstorage of metadata information, because you have to take into account that not just the data, but the metadata could be corrupted. So the other interesting thing that ZFS did is it removes volumes of partitions and it allocates the system in pools. And so you actually access the file system through a pool mechanism, much like you do a free pool of memory using malloc and free. So very much using the memory model for accessing the files, and you can see that kind of flavor from Unix, where when you talk about the Unix operating system and the variant Linux, which is loosely based on Unix, that one of the consistent models is that we treat everything as a file. And so here we can see that the opposite, where we actually take the file system and the access to the disks and we model it after memory, so that we try to do things in a consistent manner, in a way that our users can understand in terms of other programming practices. So that completes the discussion of mass storage devices. It was sort of a whirlwind tour of mass storage devices. Do we have any questions besides the intricacies of the different levels of RAID? Because I'm not prepared to discuss that, but it is in the text. Okay. So our next topic, let's see, is file systems, file systems. So the first part of this lecture is on on the interface that you see as a end user of your file system. So basically, you can think of change directory. You have directories and subdirectories, organization of directories and subdirectories. We have the read, write, execute bits in Linux or Unix, giving file permissions. You have the creation date of the file. We have when was the date the file was last updated. Those kinds of things are what we're talking about here in terms of the file system interface. We'll go through this really quickly because I think most of you, or almost all of you, will have seen this. So first, the concept of a file is a continuous logical address space where you can store data of different types. We have numeric, character, and binary, and then you actually have executable files that are actually programs that you plan to run. Again, this is not too foreign to you. I'm sure you have lots of familiarity with this. So we have many types of files. We have text files, source files, executable files, Microsoft Word files, image files. You know that there's all kinds of different categories of file formats. Associated with the file will be characteristics, a lot of which I've already mentioned. Certainly the name, it's a human readable name. You might have a unique tag or identifier with the file system, in which the file system will actually deal with the identifier because it's in a format that's easier for the management to handle it than a string name. We have the type. We talked about type, and the location where on the device it's located, the size, the protection, type, time, date, and user identification, who owns that file. Again, very straightforward and familiar to you. And then we know that information is typically stored in a directory structure. A directory structure is the most common way to organize files in terms of the user experience, but there are other schemes as well. There has been systems written in which the access of files is through queries, like a database query. And then we have hybrids where it's a directory structure, but you can also query for information. Certainly the Mac has files of that type. And actually, I think Windows has incorporated that same concept of having files that can be accessed through some search criteria quickly rather than through a straight directory structure. So if you're interested in that, both the Mac and the Windows operating system has the ability to access things in such a manner. So file operations, again, file is an abstract data type, and we know that in Linux, the file is abstracted for all kinds of devices, but typical operations is create, write, read, reposition in the file. So you position yourself in terms of reading and writing a particular place in the file, which is the seek. We have delete, truncate, and then opening and closing of the file. Notice that one of the reasons why closing a file, in particular a file handle in a lot of languages, is that the information can be cached in memory or some other type of device. And so typically a close operation will cause that information to be flushed out to the actual disk. So that's why it's important to actually do the close, because that will initiate, or typically will initiate, the flush of information out to the disk. Open files, you have an open file table, a file pointer, which is where we're currently reading and writing. You'll have a count of the number of times the file is open. This is important in multitasking systems that allow concurrent access to a file, and so that we know how many different processes are currently still accessing a file. It's interesting when this file count gets off. I'm sure a lot of you have seen that. It'll actually say you can't do something, can't write to this file, or you can't delete this file, or whatever, because it's currently being used by a process. And you look around and you're like, I have no clue which process it's being used by, and it's most likely somehow the file count got off. And then we have the dislocation of the file and the access rights. So we actually have the concept of file locking. So if you have a shared file system that many people are using at the same time, you can have various locks on it. You can consider this as the reader-writer problem, that you generally will allow the first person to access the file to write the file, and everyone else can only open this in read-only mode until the writer releases, the writer closes and saves the file, and then the readers are then allowed. The person that's doing the reading can then reopen the file with write capabilities. And often you'll have the capability that when you've written out the system, the readers will actually be notified that the file that you just opened and was locked, and we put you in read-only mode, is now available. You can open it for write if you would like. I think most of you have seen this in shared file system. Has anyone not seen this? Yeah, it's very common in shared file systems, and I'm guessing that a lot of you have seen shared file systems across multiple users and shared file accesses. So I think this is probably not too new to you, not new to you at all. And then, so the operating system is mediating access to the file. Sort of one policy was what I described just before that. And then we have mandatory or advisory. You could make it mandatory is basically that it's completely locked and we're not going to allow you to access the file at all, or advisory, which is the process is notified of the lock and then the process is allowed to decide what they want to do. So two different levels of handling that. Not really that exciting or new. File type are generally associated with an extension in a lot of operating systems. The Mac actually had a situation where they actually had a resource fork instead of a file name extension. But now I think the Mac has gone to another system. Again, it's not an extension mechanism, but some other mechanisms beyond the resource file or resource fork associated with a file. And at one time I knew the details of it, but at the moment it kind of escapes my mind what exactly the Mac operating system did to go beyond the fork resource fork. So on this page, you can see various extensions. I think you're all familiar with a lot of them, like executable files and word processing files and the like. There is extensive list of common extensions that are used, and so every once in a while you run across some extension that you have no idea what they mean, and you can usually Google it and find out what various applications are using that extension and what it is. So there is some collision with extensions where two programs will use the same extension for different purposes, but generally, we try to use unique identifiers for specific file formats. So there's different file structures that you can use for organizing your files. One is none. You just do a sequence of words and bytes put together, or you could have some type of record structure. You can think of a bunch of characters and lines separated by line feeds. You could have fixed length data where each of your data elements take up this exact same amount of storage, or you can have variable lengths where you have a mechanism for specifying the length of the data. You can have various very complex structures where it's highly formatted, or you can insert various control characters or some type of control mechanism that dictates how the data that's coming is formatted, as you actually have special characters that are inserted in there that dictates how the remaining of the characters are to be interpreted. One of the formats you can think of that does something along those lines is PDF files that have methods of specifying what kind of data is following. And then who decides that? It's generally a combination of the operating system and program. The operating system will support certain native formats, but certainly programs, like we mentioned, will have particular file formats that they utilize. So that pretty much takes us to the end of the lecture. Anyone have any questions about that? Like I said, this is pretty straightforward. Not many surprises here. You've all had lots of experience with using file systems. Okay, I don't hear or see any comments, so I'm going to go ahead and stop recording.